Modern machine learning workflows operate almost entirely through high-level interfaces. Data scientists instruct neural networks using Python, writing code that prioritizes human readability over mechanical execution. Training a large language model requires billions of matrix multiplications every second. The hardware must execute these operations at the physical limits of the silicon. This diagram of the modern software stack shows how far removed that interface is from the hardware. Python is sitting at the very top, passing logic down through PyTorch, C++, CUDA, and finally hitting the GPU registers. High-level languages carry enormous execution overhead and cannot process operations at the speed modern GPUs require. The microsecond sensitive paths at the bottom of this stack do not run on Python. They are powered by highly optimized C and C++ code. The infrastructure capable of sustaining 2024's AI relies on this lower tier. NVIDIA CUDA drivers, Google's TPU kernels, and resource-constrained edge sensors running embedded AI all operate directly on C. The current capacity of artificial intelligence is bound to a foundational philosophy of direct hardware access established decades ago. The architect behind this abstraction-free layer is Dennis Ritchie. Ritchie is recognized for co-creating Unix and inventing C to squeeze maximum efficiency out of early computers. But that efficiency was not just a design preference, it emerged from rigorous mathematical proofs. In 1968, Ritchie submitted his doctoral dissertation in theoretical computer science, titled Program Structure and Computational Complexity. The paper established that restricting the structure of a programming language is the only mathematically viable way to place an explicit bound on its computational complexity. He took the problem out of the realm of software engineering and placed it into mid-century subrecursive complexity theory. To understand why C remains the performance standard for modern hardware, we have to examine the exact mathematical proofs Ritchie formalized in 1968. General computation architectures, like unrestricted Turing machines, allow for infinite loops and arbitrary jumps in logic. This unspooling Turing machine tape illustrates the halting problem. Predicting computation length simply by inspecting code is mathematically impossible. The tape might run forever. Without guaranteed execution cycles, engineers cannot establish hardware budgets, making system failure inevitable. Ritchie realized that to guarantee execution time, he had to strip away a programming language's freedom. Without rigorous structural constraints, software is computationally unbound. Ritchie's theoretical solution was a deliberately constrained language he called loop programs. The syntax is severely restricted to primitive operations, incrementing by 1, assigning a value, and zeroing out a register. The loop1 command strictly dictates that iterations are predetermined by a register's initial state. Infinite loops are mechanically impossible. Complexity is introduced through a loop n+1 construct, which allows the program to nest loops inside of one another. A variable depth of nesting of level n corresponds directly to this instruction. Ritchie assigned a mathematical ordinal, alpha, to each loop program. This ordinal serves as an exact measure of the program's structural nesting depth. This chart graphs Ritchie's bounding theorem. It proves that a program's runtime is majorized by a calculable, strictly increasing function, f alpha, forming a hard upper limit. Larger ordinal values yield functions that majorize runtimes of smaller ordinals. Ritchie proved that the physical structure of a program dictates and bounds its maximum computational complexity. Prior to this thesis, computer scientists treated various models of subrecursive complexity as separate phenomena. This diagram plots 3 major subrecursive models: the loop program, multiple recursive, and Grozorchik hierarchies. Ritchie proved they lock horizontally into identical strata. The computational ceiling of loop programs at alpha corresponds exactly to the Grozorchik class at alpha+1. These were not competing theories. Ritchie proved that they were alternate presentations of the exact same mathematical reality. Knowing these strata are identical allows systems engineers to take abstract logic and predictably map it to concrete hardware cycles. The universe of restricted computation has a universal architecture, and Ritchie showed exactly how to quantify it. In the early 1970s, Ritchie moved from automata theory into applied systems engineering. Today, C is a general-purpose, Turing-complete language. Unlike the loop programs of his thesis, it allows for infinite loops and the unpredictable. But in building it, Ritchie applied the core insight of his 1968 work, that performance is a function of visibility. C does not hide the hardware behind abstractions. It exposes registers and memory directly. This allows the programmer to manually implement the same structural constraints Ritchie used to prove his bounding theorems. He applied this logic to the broader Unix operating system. The Unix philosophy demands small, modular tools that do one thing efficiently. Today, our distributed systems and microservices are still graded against Ritchie's standard of modularity. C didn't mandate subrecursive structures, but it provided the explicit control necessary to build them. It was Ritchie's way of turning theoretical complexity bounds into a pragmatic engineering toolkit. When researchers push modern neural networks to their limit, the computation load is staggering. Modern neuromorphic hardware rejects high-level abstractions because their execution overhead is mathematically unbound. To squeeze maximum performance out of these arrays, engineers strip away Python and return to Ritchie's structural constraints. Even as computing ventures into quantum processing, developers will require languages that speak directly to the hardware without abstraction overhead. Artificial intelligence achieves immense complexity at the user interface only because it relies on structurally bounded code executing at the hardware level. The digital future does not survive by breaking the laws of computation. It compiles and executes because we are still standing on the strictly bounded foundation Dennis Ritchie poured in 1968.